So hi, welcome back. This is about the antenna theorems that we're gonna study. If you've not watched earlier lectures, you can go into my profile and watch propagation and antenna series from there. So you can play this video in 1.x or 2x for your better experience. And so yeah, let's talk about antenna theorem. This is 1.6, 1.5, and 1.4 will be uploaded later. So okay, let's talk about, there are 6 theorems in antenna theorems basically, so we're going to talk with one by one. So superposition theorem, so like from here, from this you can just like understand it right away. So this is the point at which there are 3 transmitting antennas. Okay, there are 3 antennas: antenna 1, antenna 2, antenna 3, and they are transmitting antennas are represented by tx. So the equivalent of these antenna that produces the electric field intensity is actually the at certain point it superposes, and we get this combined effect of everything because of these transmitting antennas. So let's read it in proper engineering terms. The field intensity at any point, the field intensity at any point, due to, okay, it might be here as well because of this, and because of this. I've just kept it here for your reference. Number of transmitting antenna equal to the vector sum of the field intensity at that point due to each of the antennas. So as simple as that, as I've just mentioned, is equal to the vector sum. You have to remember, the receiving field intensity is equals to the combined effect of every transmitting antennas. So let's go to the next theorem, which is equals to Thevenin theorem. So by now you might have understood Thevenin theorem is used to actually model certain parameters into a eased form, in an easy form. So Thevenin theorem can also be used to represent antenna into an circuit of an electricity, in a simple circuit. So the antenna system can be resolved into an equivalent Thevenin system, just as I've just mentioned. So this is the antenna that you'll learn about this in 1.4 and 1.5 lectures. Generator JZ A and B. So these are 2 antennas. So yeah, let's resolve this. So you just have to memorize it at the most cases. So let's see the generator side. So VZ, you can understand, is the voltage source of the generator. RZ is the resistance of generator. XZ is equals to the reactance of generator. So even the antenna, so this part is the antenna. So XA is the reactance of antenna. XZ is the reactance of generator. RR is the, so we can just like cover it here, radiation resistance of antenna. Antenna does not have radiation, it has radiation and resistance. So RL is the loss resistance, which represents the power loss as heat, because when radiating, the antenna radiates the energy and there is like this heat which is undesirable, and this is used to represent the loss of resistance, in the form of power loss. So that is the Thevenin theorem. So let's talk about maximum power theorem. So okay, let's see, this is a circuit, this is a standard circuit. We have an source, we have an load resistance, we have an I'm sorry, it's like impedance and it's next impedance. So let's talk about this. So for this and this this circuit, this antenna, to absorb or like transmit the maximum theorem, we have to actually conjugate the resistance as seen in the source. So let's talk about this. Conjugate means, okay, if the conjugate of A plus B is equals to A minus B, antenna absorbs or transmits the maximum power from the source when its impedance is equal to the conjugate of the impedance seen looking back into the source. So okay, see there. So we have J equivalent is equals to we can like have load is equals to R equivalent plus X equivalent, the resistance plus the reactance, written in the simple form like of the network. The maximum transferred the load resistance impedance must be ZR is equals to Z equivalent, this what's it called, conjugate, sorry. So we can like actually conjugate, and if the this ZR is equals to REQ minus J X equivalent, maximum power transfer to the load is given by this. This is the next part. If we have like the resistance, the impedance equals to the the conjugate, the maximum power is transferred simply. So compensation theorem, as earlier mentioned, this is the circuit that we have created in the Thevenin format. So compensation theorem is equals to, we can represent this Thevenin equivalent circuit into equivalent generator for antenna, like so. But there must be conditions of this generator, that this generator must be zero internal, like having zero internal impedance, this generator must like be providing instantaneous potential difference that exists across the internet. Like at every instant it has to provide a potential difference like instantaneous, like it is equals to every instant, it has to be equal. So let's talk about it and explain it further. An antenna may be replaced by some generator of zero internal impedance. This has to have a zero internal impedance with generated voltage at every instant, is equals to the instantaneous potential difference that exists across the antennas. So across the antennas, the instantaneous potential difference, across the antennas should be equals to the generated voltage at every instant. As simple as that. Like you can understand it by definition as well. Zero internal impedance whose generated voltage at every instant, like it generated a voltage, at next instant, it generated voltage should be equals to the instantaneous potential difference that exists across the like the antennas. So here is the reciprocity theorem. Like so this I have written it in very summarized way. We can understand it just by like reading the definition. In any linear that follows, linear meaning follows superposition, and bilateral behaves the same if you reverse current and voltage. Bilateral means if you reverse current or voltage system, the ratio of the voltage applied at the same terminals to the current measured in a branch is the same if you swap the position of the voltage source and the measuring device. If you swap the voltage source and the measuring device ammeter, it doesn't have any like effect. The ratio of the voltage applied at the same terminal is like same, to the current measured. Voltage to the current ratio is actually same, because even if you replace the voltage like voltmeter with the ammeter. So okay, this basically the four terminal representation of antenna system. We have studied in electromagnetics, I guess, or somewhere. We can actually represent it in four terminal system. So these are the terminals: 1 dash, 2 dash. Okay, as simple as this. So we can also represent it in this form. So this is the voltage source, this is the V2. So these are the parameters that we must consider. So let's I'll give you the trick later on. Z21 and Z22, like this is kind of matrix from 1 1 1 2 2 1 2 2. Okay, so Z11 1 2 2 1 2 2, and you can like I1 I2 I2 I4 V1 and V2. That's the trick. But let's understand what is Z11. It is the input impedance at port 1 with port 2 open. Z11 is the input impedance of Z1 with input impedance at port 2 open. Because of 1 1, like imagine there is no 2, so I2 is equals to 0. So Z22 is similar, like input impedance at port 2, and like I1 is equals to 0. And Z12 and Z21 is transfer potential. So remember it like 1 2, and there is like 1 2 2 is transferred. So like just a trick. Okay, it's the transfer impedance from port 2 to port 1, considering V1 by I2 with I1 is equals to 0. It's a transfer impedance. It's like basically V1 Z12 is equals to V by I, and just mention this 1 here and 2 this, because it's a transfer impedance from like you with the reference of two ports. Z21 is transfer impedance from port 1 to port 2 with considering V2 upon V1 with I2 is equals to 0. So this I have just mentioned, and according to the reciprocity theorem, Z11 is equals to Z11 and Z21 should be equal, Z12 and Z22 should be equal to 2, I guess it's. So that's it for this video. I'll come